Hello everyone. In the last lecture we practiced the algorithm for circuit analysis on circuits with sources, voltage and current sources, and resistors. We basically explained what the equation for voltage sources and current sources are and what the equation for the resistors are, and then you started knowing those. Therefore, we can actually start analyzing circuits that include sources of voltage and current and resistors. Now, the first circuit that we did was a relatively simple circuit. In this lecture, I'm going to try to do it on two different circuits that are slightly more complicated, and by practicing that, I'm hoping that you're going to get to the habit of following this algorithm and getting it to the finish line where you can actually calculate all the voltages and currents associated with the components. Okay, so let's start with this circuit. This is actually coming from one of the examples in the book. In the 11th edition, it would be figure 218, example 2.8, page 42, in case you want to look it up in the book. And keep in mind that the way that we're doing it here is slightly different than what is done in the book. In essence, all these circuit analysis techniques, no matter what book you pick, they are the same, but the approach is slightly different. And I'm hoping that by comparing the approaches, you can actually connect the unifying concept behind it, so that you don't get confused by how one author or the other do the circuit analysis. The reason that I'm sticking to this is that, to me, this is the most universal approach to circuit analysis, and you don't have to think about how you do a circuit. If you just follow this algorithm, every time that you see a circuit, you're going to do it exactly the same, and that has some values. Obviously, there's a trade-off with following this. Sometimes you can actually end up doing more work than you have to in order to get to a solution that is associated with a certain question. But nevertheless, the price that you pay, I think, is worth the result. That is, you can basically make sure that you know how to do circuit analysis regardless of what the circuit is, and you don't have to think about how to do it anymore. At a later time, I'm going to actually take the same circuit and analyze it in three different ways, and show you that conceptually they're all the same, and then leave you with the choice of doing it however you're more comfortable, as long as you're correct, that the details of how you're doing it shouldn't matter much. Okay, so let's go back to our algorithm. We're looking at this circuit. There are two sources, one voltage source, one current source, and two resistors, so a total of 4 components. Let's identify nodes first. So ends of the components are nodes, and in this case the 3 ends on this end, they're connected to each other, so this is one node. There's another node here, there's another node here, and this is actually all one node, so we can extend that. So this is all one node. Okay. Great. So we have identified the nodes. Now we're going to move on to labeling the nodes with voltage labels. Pick our ground first. Bottom of the lower potential on our source would be a good choice. So I'm going to call that our ground, or 0 voltage. I'm going to call that V1. And call this whole thing V2. Good. So we have labeled all the nodes with voltages in the circuit. Now I'm going to move on to labeling the currents in the circuit. We have currents for each component. So this is I1, that's I2, this is I3, and that would be I4. Now we're ready to move on to the next step, which is writing KCL. So we know that the KCL are written for nodes. We have 3 nodes and 3 KCL. Like I said, the third KCL, that is for the ground, you don't have to write that one. Okay, so we start with KCL. So for that node, there's current I1 going into that node, and there's current I2 leaving that node. They have to be equal to each other. For the second node, V2 node, we have I2 going in, and also we have, in this case, I4 going in. Add them up, and that should be equal to current I3 leaving that node. And we're done with the KCL. We move on to equations for components. Now, we have 4 components and therefore 4 equations. So, for this component, the equation for a voltage source, as we explained, describes the potential difference across. So it would be V1 minus 0 is 120 volts, which means basically V1 is 120 volts. Then the equation for this component, actually let's do the equation for sources first. So for that component, the equation that describes the physics of that component is basically the current that is passing through. So I4 is passing through, and that is equal to 6 amp. Now we move on to the 2 resistors. So for the 10 ohm resistor, I2 is equal to V1 minus V2 divided by 10. And finally, I3, which is the current that is passing through the 50 ohm resistor, is equal to V2 minus 0 divided by 50. And that concludes all the equations that describe the physics of this network of components. So from this point on, all we need to do is to do the math. One approach is to take all the equations for components and use KCL and combine the two by taking all the current values in terms of voltage and put them in that. So I1 being equal to I2, we can actually do it and take I1 is equal to, now I2 is a function of V1, which is 120 volts. That would be 120, this is the result of, minus V2 divided by 10. So that's that first equation, and then here I2, which is 120 minus V2 divided by 10 plus I4, which is 6, is equal to I3, which is V2 divided by 50. So from these 2 equations, I can actually calculate everything there is to be known. So manipulate this around. That would be, I'm going to multiply both sides by 50. That would be 600 minus 5 times V2 plus 550 times 6 is 300 is equal to V2. So 6 V2 is equal to 900, and off of that V2 would be 900 divided by 6. That would be 150 volts. Now by putting 150 volts back into this equation, I1 would be 120 minus 150 divided by 10, which is minus 30, divided by 10, that would be minus 3 amp. Now I know from that equation I2 is also minus 3 amp, and from this equation I can calculate the rest. So that would be I3 is equal to 150 divided by 50 is equal to 3 amps, and finally I4 is equal to I3 minus I2 minus 3, 6 amp. So we have the solution, we have all the values. I4 is 6 amp, I3 is 3 amp, I2 is minus 3, I1 is minus 3, V1 is 120, and V2 is 150. With this, the solution, we conclude, and the solution is done. We know all the voltages. So let's count the number of unknowns in the circuit to begin with. So we had 1, 2, V1 and V2, 3, 4, 5, 6 unknowns. And look at here, we had 1, 2, 3, 4, 5, 6 equations. So the number of equations is actually equal to the number of unknowns. So we can calculate, we know that we can calculate unique values for the unknowns once the number of the equations, independent equations, is equal to the number of unknowns in our linear system of equations. And as you can see, we have calculated all the values. Now, notice that in this specific example, the value for the current I1 and the value for the current I2, they turn out to be negative. So what that means is that the assumption we made in terms of the direction of the current, which we said the current for this component is going in this direction, and for that component is going in that direction, that's actually incorrect. So the currents are going, I1 and I2 are going in the reverse direction. That's all this negative sign means. So this is to tell you that when you're making the assumption for what direction the current is going through the components, you don't have to be correct. You don't actually have to make any assumption. You just randomly pick a direction, then do the analysis, and once you're done, then you can go back and look at your assumption and figure out whether the assumption you made was correct or not. And at the end of the day, that shouldn't matter. The actual value will tell you which direction the currents are going. Now I'm going to move on to the next example where we are discussing a different circuit. I actually would like to end this momentarily and then move on to the next example so that I can clear the board. Okay, so this is the next circuit that we're going to practice our skills on. This is example 2.11 from the 11th edition of the book, page 46. In this one, we actually have a dependent voltage source. We're going to see that there's nothing different about this one in terms of approach. Okay, so again, we start by identifying our nodes. So these are all same node, as we now know. These are all same nodes. That's one node, and that's another node. pick one of the nodes and assign 0 value to that one. So this would be my choice, the lower potential in the voltage source. Again, it's arbitrary. This is what I'm going to use. We're going to say this is V1. I'm going to call that V2. Call this one V3. So all the voltages are labeled. Now, as you notice, on the circuit, the current that is passing through the component, this component, the independent voltage source, is already labeled. The reason this is done is that we have a dependent source in the circuit where the voltage of that dependent source is a function of this current. As we said, with the dependent sources, the current or voltage is actually a function of other currents and voltages in a circuit. So therefore, I am bound to use that as the label for the current that is passing through that component. I can't change that, because by changing that, then I have to change this too. So instead, I'm just going to leave it be. Otherwise, everything else is the same. I have to label all the currents passing through the component. It happens that for this specific circuit, and this specific component, the current passing through it is already labeled. Then I'm going to move on to this and call that I1. I'm going to call this I2, I3, and finally I4. And I'm done labeling all the currents and voltages in the circuit. Moving to KCL now. So we have 1, 2, 3, 4 nodes. And this node, the ground node, I don't have to write my KCL. Like I said, we can. It's consistent with the other 3, so I don't have to. Doesn't add anything to the other equations. For that node, the current IS is going into that node, and current I1 is leaving the node. For this one, current I2 is going into the node, current I3 is leaving the node. For this one, current I3 is going into the node, and I4 leaving the node. So with simple KCL, we now kind of know that these all 3 currents are actually the same, and these 2 currents are the same. Finally, I'm going to write equations for components. We have 1, 2, 3, 4, 5 components, and therefore I'm going to write 5 equations. For the voltage source, again, the potential difference across V1 minus 0 is 10 volts. That's the equation for that component. For that resistor, I1 is equal to V1 minus 0 divided by 6. For this component, again, the potential difference, V2 minus 0 is equal to 3IS. That's it. That's the equation. You don't have to treat it any different than the other source. You use the voltage here for that source. You use the voltage there for this source. It's nothing different. So I3 V2 minus V3 divided by 2. And finally, I have to be careful here, I4 is equal to V3 minus 0 divided by 3. Now, let's count the number of unknowns in the circuit. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. And the number of equations 1, 2, 3, 4, 5, 6, 7, 8. We actually have one more equations. As long as it's consistent, we don't have anything to worry about. Everything is going to come out to be fine. So let's start doing the math. Okay, so like I said, what we can do is to take values from here and replace all the currents with their equivalent voltages. So this one is actually simple to begin with. So the result of a whole thing So replacing b1, I1 is equal to 10 divided by 6. That would give me value of I1 amp. Then I3 and I4 are equal to each other, and therefore V2 minus V3 divided by 2 is equal to V3 divided by 3, and IS is equal to I1, so that's also equal to IS. So from this one, I multiply both sides by 6. I have 3V2 minus 3V3 is equal to 2V3. So from this I have 3V2 is equal to 5V3. And the only equations that I haven't used yet is that I2 and I3 are equal to each other, and V2 is equal to 3IS. So V2 is equal to 3IS. It's equal to 3 times 10 divided by 6. That would be 5 volts. Put that back in here. V3 is 15 divided by 5 is 3 volts. And now from all of that, I think we are all set. I can now calculate I4 as 3 volts divided by 3, 1 amp. I can calculate I3 as V2, which is 5, minus V3, which is 3, divided by 2, 1 amp. And we know that's also equal to I2, so I2 is also 1 amp. So we're done. We know all the values for all the currents. This is I1, this is I2, this is I3, I4, V1, V2, and V3. So 1, 2, 3, 4, 5, 6, 7 unknowns are now known. We're done analyzing that circuit too. Again, we didn't do anything new. We just followed the same algorithm and all the values are calculated. A couple of things that I want to mention at this point and finish this lecture. The math associated with this here seems to be kind of random. There's no order that is followed. I just look at these equations and kind of find out intuitively how to go about calculating these values. If you're not comfortable doing this, I'm going to actually have a lecture on how to do sets of linear equations. And that's actually an appendix in the book too. You can actually read that once I start doing that lecture, which would be the next lecture actually. This would be a lecture on parentheses, because I'm going to explain to you how to do math, which is really not a topic of discussion in this class. But I'm going to do it anyway, and hopefully you're going to get more comfortable doing this. The method that we're going to use is the algorithm that is used by, again, in computers to do sets of equations. And if you have calculators, you can, like I said, enter these set of equations in the calculator, and by push a button it spits out all the values for you, and I don't mind you using calculators. But the lecture I'm going to have on solving this is actually going to give you some insight into how the calculator does the algorithm for giving you the answers. So it might be useful or fun to see that as well. Hope you feel more comfortable with your skills doing circuit analysis. Like I said, if you read the book, this is not necessarily how the book does it, but I would like for you to follow this. If you're not comfortable doing anything else, at least get comfortable doing it this way. And the least that it has for you is that if you follow these and successfully finish step 1 and 2, which is relatively straightforward, then you get 80% of the credit, regardless of what kind of circuit you're dealing with. Thank you. See you in the next lecture.